Hey guys, this is lecture 47, installing Seaborn. So in this lecture, I'm just going to go over very briefly how to install Seaborn. So Seaborn, you can just go ahead and click the link to the IPython notebook viewer. It'll have this link on it, stanford.edu. It'll take you to this Seaborn page, so just install and get it. You can just use pip install for Seaborn. The dependencies are NumPy, SciPy, Matplotlib, and Pandas. You should already have those because of all the other installations we've done in the past. It has recommended dependencies. You might not have downloaded those yet. That's going to be stats, models, and Patsy. So you can go ahead and pip install those, and you can also do a conda install if you ended up downloading the Anaconda distribution. Seaborn is a really great visualization library for statistical datasets. Here's just the example gallery off their website, and we're going to learn how to make a lot of these types of plots for analyzing our data. Another nice thing about Seaborn is you can choose different color palettes, has a lot of options for you, and it even has colorblind options in case you're colorblind, so you can explore that as well. But as far as installing Seaborn, it should just be a simple either a pip install and then Seaborn, or conda install Seaborn if you downloaded the Anaconda distribution. Alright, so that's about it. Just go ahead and install Seaborn, and we'll get started with learning how to visualize our data in the next lecture. I'll see you there. Hey everybody, welcome to lecture 48, histograms. So in this lecture we'll be learning about how to use data visualization to create histograms. Alright, so this is going to be the first lecture in the data visualization section. So we're going to do quite a few imports here. First we're going to do our standard imports. So that's going to include import NumPy as NP. Then we're going to import Pandas as PD. And then we're also going to need from numpy.random import randn. Okay, so we got those imports. Then we also need some stats imports. So I'm going to say from SciPy import stats. And then we're also going to need the plotting imports. So I'm going to import matplotlib as MPL. We're going to import matplotlib.pyplot as PLT, and then we're going to import Seaborn as SNS, and that's the convention for Seaborn. And then finally we're going to give a command, matplotlib, that we've done in the past, inline, and this %sign matplotlib inline, that allows us to see our plots in IPython notebook. And there we go. So you can go ahead and see there's in the link for the IPython notebook viewer, all these imports are in one cell, so you can go ahead and feel free to copy and paste that for all the data visualization lectures. I'll be doing that in the future. Alright, so first of all, if you want source information for what a histogram actually is, you can go ahead and just go to this link, URL, it's the Wikipedia link for histogram. If you're a little fuzzy on your stats, you can go ahead and just check it out. And this will give you all the information you need to know about histogram. So I'll assume for the rest of this lecture that if you felt unfamiliar with histograms, that you can read about it on the Wikipedia page. Otherwise, I will continue. They're pretty straightforward things. So let's go ahead and create a random normal distributed dataset. So I'm going to say dataset 1 equals rand n, and we'll have 100 data points there. And now I'm going to plot a histogram of that dataset. And in order to do that, all I got to do is plt.hist, so I'm using matplotlib.pyplot, and I'm calling the hist method on it, and I'm going to input my dataset to get that histogram. Okay, and there we have it. So if you notice, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bins. So 10 bins is the default number of bins that plt.histogram or .hist will create. So it's going to separate all your data, no matter how many points you have, into 10 equally spaced bins. Alright, great. So let's go ahead and make another data set. We'll call this dataset 2. And we'll have this one only be 80 points. And we'll also plot a histogram of it. Hist. And we'll say data set 2. And in this case, I want the color to be red. And I want it to be a particular shade of red, so I can pass the color argument. And there's a color called Indian red, and I will choose that. So let's go ahead and check that plot. Okay, so there's that histogram, and it's now the Indian red color. So, what if I wanted to see both these histograms on the same plot? I can totally do that. So what I can do for that is say plt.hist dataset 1. And since they both have different numbers of data points, so this is 80 data points and dataset 1 is 100 data points, I have to normalize my plots. So I can do that by saying, passing the argument normmed equal to true. I'll set dataset 1 to have the color Indian red this time. And I'm also, since I'm going to be plotting them right on top of each other, I'm going to want some transparency there. So to control transparency, the argument is alpha. So if I set my alpha equal to 0.5, you can set your transparency from 0 to 1. So 0.5 is that transparency level. So you'll be able to see, in a sense, through the histograms, even though they're on the same plot. And you'll see what that looks like in a second. And let's get some more bins, and I can get more bins. The default is 10, but I'm just going to double that. I'll set bins equal to 20. So that's another argument we can do. And then in the same cell, I'm going to say plot hist, and I'm going to plot dataset 2. Going to set the normalization equal to true, so they're both normalized. I won't worry about the color. I'll just have it use its default blue color for dataset 2. But again, I will set it to have some sort of transparency using alpha, and I will also make that second data set have 20 bins. Alright, so let's go see what this looks like. And there you have it. So we have the two histograms now plotted, and they're stacked on top of each other, and where they overlap, since we set alpha equal to 0.5, there's a little bit of transparency there, and you can see that it creates a purple color automatically where the histograms go over each other. Great. So now let's learn how to do something similar with Seaborn and try to get some more information out of this. So I'm going to make two more data sets. I'll say data 1 equals random, and let's get a ton of points. So let's say 1,000 points, and we'll do the same for data 2. We'll have that equal 1,000 points. Let's go ahead and do that. Great. So now I have these two very large data sets. So I can represent this as a joint distribution using joint plots. So the way we do this is we call Seaborn, SNS, dot, and then we can call the method joint plot. And what I'm going to do is I'm going to input my two data sets. So I'm going to say data 1, data 2. And let's see what that looks like. Great. So now we actually have a joint plot of both data sets. So you can see the distribution of dataset 1 and the distribution of dataset 2. It gives you your p-value, and then it individually plots all the data points and where they overlap. So we can also do this if you don't want to see all these points. You can use hex bins for a more concise picture. So let's go ahead and see how that works. So SNS dot joint plot again. Again, we're going to put both data sets. So I'm going to say data 1 and data 2. And now I can pass the argument kind and set that equal to hex to get a hex plot in the joint distribution. There we go. And so that will be a little easier to read and give you a little more visual information than just all these points themselves. Alright, great. So that's the basics of histograms. If you just want to get a run-of-the-mill histogram, all you got to do is say plt.hist, input your data set, and you can check the documentation for PyPlot if you want to know more arguments to pass. There's colors. Remember to do normed if you want different data sets with a different number of points on the same plot. And then you can do joint plots with histograms on them using sns.jointplot, and you just pass both your data sets there. And if you want a hex bin on this joint plot, you just say the kind and pass hex. Okay, great. Next we'll learn how to use kernel estimation plots. Hey everybody, welcome to lecture 49. So in this lecture we're going to be learning about kernel density estimation plots, otherwise known as KDE plots. So if you're a little fuzzy on your statistics and can't quite remember how exactly the kernel density estimation plots work, you can go ahead and just check out the Wikipedia page on kernel density estimation plots. They're basically just ways to estimate the PDF, the probability density function of random variables. And you can see here, here's a histogram on the left, and on the right is the kernel density estimate. And these KDEs are constructed from just Gaussian distribution plots on every data point, and then you just sum them up. So what we're going to do in this lecture is manually create this plot by summing up those Gaussian curves, and then we're going to use Seaborn to do the shortcut method on that. And we'll go over a little bit of bandwidth selection. We'll be using the Gaussian approximation for it. Alright, so let's go ahead and get started. We're going to have to do a lot of imports like we did last time. I highly suggest you just edit copy, edit paste like I'm doing right now from the IPython notebook viewer. So we just have our normal imports, the stats imports, the plotting modules, and the libraries we'll use. Let me fix that. Okay. And we have matplot inline, so the plots appear in the IPython notebook. So let's go ahead and start off with making a KDE plot manually. Let's just start with a simple rug plot, or some people also know them as carpet plots. All a rug plot does is it just puts a tick wherever a value occurred. So in order to plot something, we need something to plot, so let's get our data set. And let's create that from rand n 25 points. So we have our data set there, and then we can use Seaborn rug plot, so sns.rugplot, and call it on that data set. And now we have our every tick is a spot in that data set, a value in that data set. So to make it a little clearer, let's go ahead and set some y limits on that. So I'm going to say plt.ylim, and then I can set the lower and the upper y limits. So I'm going to set it from 0 to 1, so I just get a bunch of little ticks. Okay, great. So every tick is a point on that data set. Excellent. So let's go ahead and plot a histogram on top of that. So the way to plot a histogram is you can say plt.hist, input the data set you want to plot. In this case it's just called dataset. And if you want to make it transparent, you can do that by passing alpha. So you can put an alpha from 0 to 1, 0 being totally clear, 1 being totally opaque. And in this case I'll just use a value of 0.3. And since I also want to have the histogram on top of my rug plot, I will say my rug plot in the same IPython notebook cell, and I will pass my data set through it. Scroll down a bit. Okay, great. So it's actually pretty obvious now what a histogram is doing that we saw last time. Basically, for every bin, it's just counting how many ticks are in each bin. So for instance, the bin all the way on the left has 1 tick in it, so the bin is 1 high. If we move to the next bin, it has 0 ticks, so it's 0 high. and etc., etc. It's just counting the number of ticks in each bin and then making the bar that high. Okay. So the kernel density plot, what it's going to do, it's going to represent each of these tick marks with a Gaussian basis function. So we're going to do this manually first before we see Seaborn's shortcut. So this is going to be a big cell. So we're going to say rug plot, SNS rug plot, pass the data set, and then we're going to set up the x-axis for the plot. So we need a min and a max. So I'm going to set the x minimum to be equal to the minimum value in that data set minus 2 for some range, and I'm going to do a similar thing for the maximum. I'm going to set the x max to data set, the max value in there, plus 2. Okie doke. And in that same cell, I'm going to set my x-axis. So I'm going to set x-axis to be 100 equally spaced points from x-min to x-max. An easy way of doing that is just by using np.linspace, so linear spacing. And the inputs here, I'm just going to go from my start to my stop, and then the number of points I want. So I want it to start at x-min, stop at x-max, whoops, and I want 100 equally spaced points. For setting up the bandwidth, I'm just going to use the bandwidth estimation, which, if you're unfamiliar with, you can go down and see here again on the Wikipedia page, the practical estimation of bandwidth, and we're just going to be using this equation. So this equation is just the bandwidth is equal to 4 times your standard deviation to the power of 5 over 3 times n, which n is the number of points in your data set, and all of this to the power of 1 over 5, or 0.2. Okay, so let's put that estimation equation into Python. So I'm going to call it the bandwidth. And first we have that 4 times the standard deviation of our data set. So 4 times, and we can get the standard deviation just by calling std on that data set. And then all of that was, well, the standard deviation to the power of 5. So we have that part, and then the denominator of that estimation equation was 3 times the number of points in the data set. So to get the number of points in the data set, I can merely just check the length of the data set. So I can use len on the data set. And remember, that whole thing was to the power of 1 over 5, which is the same as to the power of 0.2. Great. So next we're going to create a list for those kernels. Remember, we're going to have a kernel density estimation plot, so we're going to set a little Gaussian plot for each of those kernels. So I'm going to make a kernel list, and I'll set it as an empty list, and now I'm going to make a little for loop to build out that list. So I'm going to say for every data point in my data set, I'm going to do 2 main things. I'm going to create a kernel for each point and append it to the kernel list. So how do I do that? Well, I'll create an object called kernel, and I'm going to use the SciPy stats library to do that. So I'm going to say stats.norm, because it's going to be normally distributed. I'm going to take it on that data. It's going to make a normal continuous random variable distribution. So it's going to take that data point, so basically that singular tick, and it's going to make a normal distribution curve using the bandwidth estimation that we just figured out. And then the kernel will be the probability density function method called off using the x-axis that we created earlier. And then once we have that kernel, let's go ahead and append it to the list we made. Alright, so that's the first part. Create a kernel for each point and then append it to the kernel list. And then let's go ahead and set up a scale for plotting. So I'm going to set the scale. I'm going to say every kernel, basically every Gaussian basis plot on each of those kernels, which we're labeling right now as just kernel. I'm going to set it to be divided by the max of the kernel value. And then I'm going to resize everything by 40% just so it reaches a max of 0.4. And then we'll plot everything. We'll say plt plot along the x-axis. Go ahead and plot that kernel. I'm going to set the color equal to gray. And I'm going to make it a little transparent since, remember, we have that red plot on top. After all that, I'm going to just set my y limit axis like we did earlier. I'm just going to set it from 0 to 1. So before we click enter, let's make sure we got everything right. We're going to create a rug plot, set our x minimum and maximum values, then using linspace, create an x-axis values, 100 linearly spaced points between the min and the max, using the practical estimation of the bandwidth, Gaussian approximation, or the normal distribution approximation basically. We created our bandwidth, created an empty kernel list, and then for every data point in the data set, we created and plotted that kernel. Alright, so let's check if this worked out. And there you have it. So you can see the ticks in color here, and you can see the Gaussian basis function plot for all of them. So that's pretty cool, and you notice they all peak at 0.4 since that's what we set it to be. So we normalize everything by the max, and then we set it to go to 0.4. Alright, great. So now that we have that, to get the kernel density estimation plot, we need to sum all those. So how do we do that? We can say the sum of KDE is equal to, using NumPy, np.sum of that kernel list we made, and we'll do it along axis equal to 0. And now we can plot that. So I'm going to say fig for figure is equal to plt dot plot, and I'm going to plot along the x-axis. I'm going to plot my sum of all those kernel densities, and then I'll set the color to be equal to Indian red like we previously did before. And then I'm going to add a rug plot just so we can get a good look at all the ticks. So I'll say rug plot dataset, and then plt, let's go ahead and get rid of the y ticks so there's no confusion. So this will get rid of all tick marks by just putting an empty list there. And then we can go ahead and title our plot by saying sup title, and we'll label this as the sum of the basis functions. So we're going to sum up all those Gaussian basis functions. Alt enter, and what do we get? Alright, great. So now we have the kernel density estimation plot by adding up all of these Gaussian functions for each of the tick marks. Great. So we did it the long way. We can do this in one simple step using Seaborn. This is why Seaborn is so awesome. We can use sns.kde plot and just input our data set. And there you have it. So you can see that Seaborn can do a kernel density estimation plot just in one simple go. And we can adjust the bandwidth of the Seaborn KDE plot to make it less, well, more or less sensitive to high frequency data points, or data sets, I should say. Okay, so to show you what I'm talking about, let's go ahead and make a rug plot. So I'll make another rug plot using my data set, and this time I'll set the color equal to black so it's really visible. Won't make it transparent. And then I'm going to plot kernel density estimation plots for various bandwidths. So I'm going to say for BW, or bandwidth, in the NumPy range and p.range, let's go from a bandwidth of 0.5 to 2 in steps of 0.25. So for each of those bandwidths, I'll make a kernel density estimation plot by passing sns.kd_plot on my data set. The bandwidth argument for that, we can just say it's BW equals BW. I'll set the LW value to be equal to 1.8, and I'm going to label each of those plots by their bandwidth value, and you'll see what that looks like in a second. So let's go ahead and plot all of those. So now you can see, based on your bandwidth choice value, what your kernel density estimation plot would look like if you specify a particular bandwidth. And just running it with no bandwidth specified, Seaborn will automatically get the bandwidth estimation for you. Alright, great. And then we have all our ticks down at the bottom of that rug plot. We can choose different types of kernels. So for that information, you can go ahead and check out this URL. So this is just a Wikipedia page for what a kernel is in statistics. So if you're feeling a little fuzzy on the statistics of what we just did, you can go ahead and check out that. So let's go ahead and check it out right now. So we can check out on the Wikipedia page the different kernel functions here. And so you can use these different functions in Seaborn if you want to. So let's go ahead and see how all these little different functions work. So we can say, let's go ahead and create some kernel options. So I'll make a list called kernel options equal to, so you have a bunch of different kernel options like cosine or EPA. Let's make a Gaussian. Whoops. And you can check out the Seaborn documentation or just the kernel Wikipedia page if you want to know more about each particular kernel option. But if you're interested in this, you're probably already a pretty advanced user of statistics. And then for kern in kernel option, we will plot, sns.kd_plot. We'll plot that data set, and I will set the kernel type to kern. So for each kern in all of these options, we're going to do all of these, and then I will label it the kern type. So let's go ahead and see what Seaborn can do. And there you go. So you get a bunch of different types of kernel density estimation plots based on the kernel type you want to use. And you can go ahead and read more about it either in the documentation or just in the Wikipedia statistics page for what kernel functions look like. Alright. Another quick thing we could have done is do some shading. So if you wanted to shade all of these to see where they overlap, you could have set shade equal to true here. Let's do it again. And there you go. You have shading on all of them. So that's something you can do. If for some reason you wanted to plot on the vertical axis, so the y-axis, you can do that as well. I'll show you an example. You can say KD plot dataset and just set vertical equal to true, and you'll be plotting on the vertical axis. Okay, awesome. Finally, we can use a KDE plot also to create a cumulative distribution function, or a CDF of the data. If you're feeling a little fuzzy on that one as far as statistics goes, you can just check out this URL or check out the link on the IPython notebook. And I will go to this link right now. So you can check out the CDF. So it just describes the probability that the variable x is going to be found in that distribution. So if you're familiar with statistics, you're probably familiar with a CDF already. So if I wanted to plot that, I could just say SNS KDE plot your data set. And if you want the CDF, you can just set the argument cumulative equal to true. And there you have your CDF. Alright, great. You can also do KDE plots for multidimensional data. So that would be a multivariate density estimation. Alright, so in order to check that out, we are going to create a new data set. So let's go ahead and make the mean, or the center of the data. So I'm going to make an object called mean, and I'm going to set the mean at 0, 0. So the x and the y mean on that data set. I'll set the covariance as well. I'll just set 2 pairs. I'll go 1, 0 and 0 to 100 as those covariances. And now let's go ahead and create a data set using NumPy. Let's go ahead and call it dataset 2. We're going to say np.random, and then we're going to call multivariate normal. So multivariate normal, and here we can pass the mean, the covariance, and the size we want. So this is going to draw random samples from a multivariate normal distribution. So let's go ahead and pass our mean, our covariance values, and the number of points we want. Let's just make it 1,000. And now it's been a while since we used Pandas, which we took a whole bunch of sections to learn about, so we can bring that back. Let's go ahead and put that data into a data frame. So we'll say pd dot data frame, and I'm using pd because I don't believe we imported series and data frame separately. So I'll say dataset 2 columns equal to xy, and I'll go ahead and plot this using a KDE plot. And so notice the really, really great thing here before I click enter, you're using Seaborn in perfect sync with a Pandas data frame. Let's go ahead and see what happens. And there you have your multivariate density estimation using the KDE plot and a straight up Pandas data frame. If you wanted to, you could have also passed 2 vectors separately. So you could have said sns.kd plot, and we could have just passed the x and the y vectors. So I could have said dframe.x, dframe.y. So instead of just passing the whole data frame, pass their 2 vectors separately. Go ahead and see that, and you'll get the same thing. Another option you can do is you can shade. You can do that just by passing the shade argument, set it equal to true, and now you have it shaded instead of those contour lines. And you can again specify bandwidths. So just like we did in the other plots up here, as far as specifying the bandwidths, you can do the same thing. So let's scroll back down. You can say KDE plot your dframe, and again set bandwidth BW equal to whatever value you want. So I'll make it some ridiculous value 1 just so we can see the heavy change. And there you can see that bandwidth change on your multivariate KDE plot. Or if you just want to use that the Silverman estimation that we used before, you can actually call it by a string. So you can say KD plot, call your data frame from Pandas, and then set your bandwidth equal to the string Silverman, and that will run your Silverman estimation bandwidth, or Silverman's rule of thumb, it's also called. And there you have that bandwidth. Okay, and then lastly, we can also create a KD joint plot. So similar to the hex bin plots we saw before, I can say SNS.jointPlot, and let's go ahead and we can label it X and Y for the axis. Pass your Pandas data frame, and then if you want a kernel density estimation plot, you can label it as, pass the argument kind, and then pass KDE as the kind of joint plot you want. So this is the same as the joint plots we did before, except now we're specifying it that it's a kernel density estimation plot. Let's go ahead and do that. And there you have it, your two multivariate kernel density estimation plot. All right, so we just went over a ton of stuff. Go ahead and look back, make sure you understood all of it. This particular lecture was really dependent on your understanding of certain statistics. So go back and look up on Wikipedia those Wikipedia links if you're feeling a little fuzzy or don't remember all of those or just need to learn them in general. And then you can come back and then really understand the different plotting techniques we just did. Okay, so that was kernel density estimation plots. Up next, we're going to learn about combining plot styles using distplot. Okay, I'll see you there. Hey everybody, welcome to Lecture 50, Combining Plot Styles. So in this lecture we're going to be learning how to combine plot styles. I've already copied and pasted the imports we're going to be using for the data visualization section. So you got your normal inputs, the stats library, and then the plotting modules, as well as matplot inline command. So this lecture will be quite a bit shorter than the last lecture, and we're going to learn a lot. So we're going to learn how to combine different plot styles. So let's get something to plot. Let's go ahead and make a data set. We'll set that equal to this random 100. So let's get 100 points. And then to make a combined plot, Seaborn has a built-in DIST, so distplot. And this allows us to combine plots. So if I pass my data set through this and I set my bins equal to 25, by default bins are set to 10 in Seaborn. I'm going to hit Alt Enter. So by default this DIST plot combines a kernel density estimation plot, this line that we discussed in the previous lecture, with a histogram, which we also discussed in previous lectures. Great. So we can also choose whether it's a rug plot, a kernel density estimation plot, or a histogram. Those are all input arguments to distplot, and we can either turn those plots on or off. To show you what I'm talking about, let's go ahead and call the DIST plot. Call it on the data set. Again, set your bins equal to 25. And now what I'm going to do is I'm going to set rug equal to true, so I can see a rug plot. And I'm going to set hist equal to false, so I don't see the histogram anymore. Let's go ahead and hit Alt Enter. And so now by default it showed the KDE, but I set rug to true, so it's showing my rug plot, and it's not showing the histogram anymore because I set hist to false. Excellent. So let's say I want to control specific plots within the combined plots. So if I wanted to do, maybe set a certain color to the rug plot, or set certain parameters on the KDE plot, I can do that by passing dictionaries into distplot. So I'll show you how to do that now. So we can call SNS distplot, call my data set, set the number of bins, let's call it 25, And what I can do is I can pass dictionaries. So the way we can do that is by having a plot underscore KWS argument equal a dictionary. So what I mean by that is if I want to edit my KDE plot, and hold on a second, I forgot the S there. Like I was saying, if I want to edit my KDE plot, I'll set KDE and then underscore KWS for those arguments. And I'll set those arguments equal to a dictionary. So I have my color key, and I can set that equal to a color, so I'll select Indian red. And then I could also make a label specifically for the KDE plot and set that key equal to KDE plot. And then let's say I wanted to also edit my histogram that came along with the dist plot. I can do that just by saying HIST, again, underscore KWS, equal, and then I can pass a dictionary, again, with certain controls. So let's set the histogram color to blue, and let's label it. So set the label key, and its value will just be HIST. I'll capitalize it. Okay, let's go ahead and see if that worked. Great. So now you can individually control the subplot, not quite subplots, but each individual plot in the combined plot, just by passing dictionary and then the plot subname underscore KWS. Great. All right. So again, we've learned so much about pandas, and Seaborn works really well with pandas. We can use pandas data objects for this. So I can say from pandas, let's go ahead and import series. And let's create a series from a data set. So I'm going to say ser1 equals series from the data set, and I'll set that series name to be the string my underscore data. And then let's go ahead and see what that series looks like. So there's my series made from those 100 points. Great. And now we can use Seaborn, sns.dist plot. You can pass a pandas series, and again, just let's say bins 25, and it'll plot the pandas series. So Seaborn works fantastically well with pandas. It's a great data visualization library that works really well with pandas. Okay, so let's go ahead and go to the next lecture where we're going to learn about box and violin plots. I'll see you there. Hey guys, welcome to lecture 51. This lecture will be on box and violin plots. So I've already imported on my first cell all the imports we've been using for the data visualization section. And in case you're a little fuzzy on box plots or violin plots, you can go ahead and check out this link. It's just a link to the Wikipedia page for box plots. So they're pretty straightforward. It's just another way of representing a probability density function using quartiles. So you can see here, this figure kind of shows how the probability density function relates to the box plot. So let's just take a look at that. Okay, so let's find out how to make these box plots. All right, so let's just start off with two data sets. So I'm going to make data 1 equal ran n, just 100 points. And I'm going to do the same thing for a second data set, ran n 100. And now let's go ahead and create a box plot. So the way we can do that using Seaborn is SNS dot, and you probably guessed it, box plot. And let's go ahead and pass both data sets, and we can do that using a list. So I'm going to pass data 1 and data 2. Let's see the result. Alright, and there you have your box plot. So if you notice here, on top of this blue box plot, you still have an extra outlier point, And if you want to include those into the range of the whiskers, you can. And you can do that by calling boxplot, again, both datasets, data 1 and data 2, and this will be passed as a list, so put them in brackets. And then you can have the whiskers include any outliers by setting it equal to npy.inf infinity, so numpy infinity, and there you go. So you can see now the whiskers on the blue box plot have jumped out to that outlier, and so now your whiskers include all your outliers as well. You can also set it horizontally if you wished. So box plot, let's just do one data set. We'll just do data 1, and if we want to set it horizontally, we can just pass the argument vert for vertical equal to false, and now you have a horizontal box plot. Great. So while box plots are really useful and great, especially for things like financial data and stocks, we can also use violin, or some people call them viola plots, and that combines the simple format of a box plot with the information of a kernel density estimation plot. So let's see how we can make those. First, I'm going to show you an example where the box plot won't give you the full picture. So in order to do that, I'm going to first make a normal distribution. I'm going to rename data 1, and I'm going to use stats.norm to make this distribution. And so what we're going to do is call it from input 05, and then I'll use .rvs to get 100 points from that distribution. And then I'm going to also make 2 gamma distributions, and then I'm going to use I'm going to concatenate them together. So I'm making some really specific data sets to show you the example of when a box plot won't give you the whole picture. So don't worry too much if you don't get how I make this second data set. It's not actually a big deal as far as learning how to create a box and violin plot. So I'm going to use NumPy concatenate. We've actually learned how to use that before. And I can call the stats gamma to get a gamma distribution. And I'll just run it 5, and I'm going to get 50 points. And I'm going to subtract 1 from that. And then, since I'm going to use concatenate, I'm going to make another gamma distribution using stats. And again, I will run it with 5. And in this case, I will also call 50 points. But what I'm going to do here is on the second gamma distribution, I'm just going to multiply it by -1. Alright. And then I'm going to box plot both data 1 and data 2. So I can do that by saying sns.boxplot, and then pass a list of both those guys, data 1, data 2, and let's set our whiskers to include any outliers, so I'll have them go to infinity. Oops, and I spelled gamma wrong here. There we go. Okay, so if you just quickly look at these two box plots, you could say that both distributions are pretty similar. Just one's a little wider than the other. But if you want to get the full picture, you might need to look at the kernel density estimation plot. So that's where the violin plots come in. They're going to basically combine a KDE plot with a box plot. So in order to do that, I am going to call violin plot. So SNS violin plot, and then let's go ahead and call data 1 and data 2. And now you can see the distributions look actually quite different. So this is pretty revealing. Here it's clearly a normal distribution, and then you can see here the set of the two gammas, one positive and then one negative. So the box plot definitely doesn't show you that whole picture there. So violin plots can be pretty revealing for your data. And just like we used for the KDE plots, we can also change the bandwidth of the kernel used for the density fit in a violin plot. And you can do that just by passing your data and then specifying the bandwidth. So if I specify some ridiculously small bandwidth so it's super sensitive to the frequency, that can affect your violin plot. So you can decide what bandwidths you want to do if you want to input specific bandwidths into your violin plots, just like we did for kernel density estimation plots. So also, kind of similar to a rug plot, you can include the individual points. So what I mean by that, to show you an example, is let's have our violin plot, data 1. So here's our violin plot, data 1, and let's say I want to include, just like a rug plot, all the individual points. Well, I can do that either with points or sticks. So I can pass the argument inner equal to stick, and now I should get a line, and all these lines are individual data points along this distribution. So it's basically bringing the idea of the rug plot to a violin plot. Alright, and that's pretty much it as far as box and violin plots. Just remember you can call them using either violin plot and box plot, and it's always good to keep in the back of your mind about the kernel density estimation plot, just to make sure you're getting the whole picture of your data. Okay, and that's about it. In the next lecture, I will be going over multiple regression plot. Alright guys, let's go ahead and start lecture 52. And this will be on regression plots, or multiple regression plots. Okay, so I've already filled out my cell with the normal inputs and imports for the data visualization section. And we're going to learn how to visualize multiple regression with LMplot. So Seaborn comes with some example data sets, and we can use those in conjunction with a Pandas data frame. So let's go ahead and upload one of those data sets. So I'm going to make a data frame called tips, and from Seaborn SNS call load underscore dataset, and then the name of this data set is tips. Wait for it to load. Alright, once it's loaded, let's just go ahead and check out the first 5 rows by calling tips head. Okay, so what's in this data set? We got a total bill, the tip left on that bill, the sex, whether the person was a female or male, were they a smoker, the day they paid their bill, the time of their meal, and the size of the party. Alright, great. So now that we have that information, let's go ahead and plot it. So let's plot the total bill, or the tips versus the total bill. So we can do that using SNS, and we're going to use LMplot to do a regression plot here. So let's put in total underscore bill, and we'll plot then tip, and then the data frame is going to come from is tips. So let's go ahead and plot that. Alright, awesome. So first off, we can see a scatter plot of all the points on tip versus total bill, and then we see the linear regression line, and that's just an estimated linear fit model for all the data. So this is the linear regression fit for all this data that's been scattered on this plot. Alright, so just like before, we can use dictionaries to edit individual parts of that plot. So to show you an example of this, let's go ahead and say SNS LMplot. Again, we're going to do the total bill, and then the tip left, and we're going to grab it from the tips data frame. And now, if you remember from previous lectures, we can say the name of the plot type underscore KWS, and now I can set a dictionary for some additional arguments for each individual plot. So let's say I want my scatter plot to use a particular marker type. I can say marker as an argument and have that key have the value of O. And you can look at the documentation. You can also put in stars and other different markers for scatter plots. And then I'm going to set the color of the scatter plot, have the key color be Indian red. Alright, and then for the line, for that linear regression plot, let's see, I'm going to set some of those. I'm going to set the line width. So I'll set that equal to 1, and then I'll set the color key equal to blue. Well, not equal. I'm sorry that I keep saying that, but it's a dictionary, so it's your key and then your value associated with it. You're not actually typing in equals. Alright, so let's go ahead and see how that plot works out. And there you go. So now on this multiple regression plot, you've been able to individually pass arguments on the scatter plot and the linear plot separately. Okay, so this is just a first order trend line. We can also do multiple higher orders if we want to do some quadratic fits to this data set. So for instance, the way I can do that is by passing order. So I'm actually going to do it on the previous cell. Since we'll keep all the information the same, I can indicate what order polynomial fit I want. So if I wanted a fourth order, I just pass the argument order 4. So let's see how that changes our fit. And so now we have a different fit on the data. So you can use that in case you don't want a linear fit. You can just specify what order fit you want. Okay, so we can also just not fit a regression at all. We can just have it be a pure scatter plot. So we can say SNS LM plot. Again, the total bill, the tip, and then the data frame we're going to get it from is tips. And then if we want to just get rid of the regression fit, I can say, whoops, I can pass fit underscore reg equal to false. And if we do that, let's go ahead and see the plot. And so now we basically just have a scatter plot of all the data. So LM plot also works on discrete variables, such as the percentage of the tip. So let's go ahead and see what that looks like. So to get the percentage of the tip, let's go ahead and just remind ourselves what the data frame looks like again. Alright, so we got the total bill, the tip, and then the other columns. So let's go ahead and make a new column. So we'll say tips, and I'm going to say tip underscore PECT, so it's a tip percentage. And I'm going to set that equal to 100 times tips, the tip column, divided by the tips total bill. So now I'm just making a new column onto this tips data frame called the tip percentage. So what percentage of the tip was the total bill? I'm sorry, what percentage of the total bill was the tip? And so I'm going to say 100 times tip divided by the total bill to get that number. So let's go ahead and do that. And now let's take a quick look at that column. Here we go. So for instance, in row 0, the total bill was almost $17. You had a $1 tip, and that's about 6% of the bill. Great. So let's go ahead and plot that then. Since we're going to check how it works with discrete variables, we can do SNS LM plot. And now I'm going to plot the size. So I'm going to plot tip percentage versus the size. So I'll have my X be size, and then my y be tip percentage, or tip PECT, and then again the data frame we're grabbing this information from is called tips. So let's go ahead and see that. And so there you go. So now you have discrete variables, and they've been plotted using LMplot. So here's the size of the party, and then the tip percentage they left behind. If we want to make this a little easier to read, we can add a jitter to it. If you're unfamiliar with jitter, you can go ahead and check out the Wikipedia link for jitter. So I'll leave it there for you guys. If you're already familiar with jitter, or after you've read that link, come back. And the way to add jitter is, again, we'll run size, tip, tips, and then we can set the x jitter. For jitter related to the x-axis, we'll just equal to 0.1, just to get a light jitter. So it should spread out our data a little bit more. There you go. It just makes it a little easier to read, so not as many points overlap with each other. All right, great. So we can also estimate the tendency of each bin. So each bin is the size of the party in this case. So if I wanted to do that, I could say SNS LMplot. Again, size for the x-axis, tip underscore PECT for the y-axis. Data frame I'm going to use is tips. And now I'm going to say x estimator equal to NP or NumPy dot mean. All right, and so now this shows the estimate for the tendency of each bin, depending on what tip percentage for the size of the party they'll leave behind. So it looks like there's a little more variance for party sizes of 1 than of 2 through 4, which is a bit interesting. Another thing we can do with LMplot is we can use the hue facet to automatically define subsets along a column. So I'll show you an example of what I mean by that. So I'm going to say SNS.LMplot, and in this case I'll have the total bill be the x-axis, and then the tip percentage be the y-axis. Again, I'm grabbing it from the tips data frame. And now I'm going to pass the hue argument, HUE, and I'm going to set the hue equal to the sex column, so whether they were male or female. And then I'm going to add a markers argument as well, and I'm going to pass a list for markers. So in this case, I'm going to use X markers for the female and O markers for the male. And using the hue argument, we're going to automatically create hues for the sex column. So let's go ahead and see what happens when I do that. Okay, so now I basically have two regression plots right on top of each other. The green is the male, and the blue X's are the female. So I got both scatter plots and then both linear regression plots. So this could be a really interesting case study in who tips more, females or males, and what's the tendency for the tipping amount. All right, so what if we wanted to know, does the day make a difference in how much the tip is? So we can do that as well. I can ask for the regression plot. Let's go ahead and set X to the total bill. Set Y equal to the tip percentage. Take it from the tips data frame. And in this case, I'll use hue again, HUE. And now I'm going to set it to the day. And I'm not going to pass the markers argument. I'll have them all be the default, same scatter marker. All right, so let's go ahead and pass hue for day. And now we can see whether the tip percentage changed on the total bill versus the subsets of the column for day. So how much did people pay percentage tips on Friday, what was the relationship between Saturday and Sunday versus just Thursday. So you can get a lot of interesting information off these multiple linear regression plots. Alright, and then finally it should be noted that Seaborn also supports what you can call local regression model fitting. So this is definitely a more specific statistical analysis technique. We won't be using it in any of the projects, but in case you're familiar with statistics, you should know that Seaborn can do this. Sometimes it's called LOES or LOESS, so you can look that up too. So let's go ahead and see what local regression can do for us. So we can say total underscore bill, tip percentage as the y-axis, tips is the data frame we're going to graph from, and so we'll set LOES for local regression equal to true. And now I'm going to edit my line, and if I want to edit my line I can do that by saying line underscore KWS as we've done in the past, and like we've done in the past as well, set a dictionary. So I'll set the color key, set that to have a value of black so it shows up against the scatter plot. Okay, and that's what your LOES line looks like. Again, this is a pretty specific statistical thing, so don't worry too much if you don't quite understand what just happened. It's really more of a specific task that you may want to do in the future. Okay. Now let's zoom out a bit. LMplot is actually using a lower level function called regplot or regplot, depending how you want to say it, regplot, which is just for regression plots. So let's go ahead and look at that lower level function. So sns.regplot for regression plot, and then I can insert total bill, the tip percentage, and tips. And so regplot is the lower level function that LMplot was built on top of. So this is the more robust, if you will, plotting function. So here we have tip percentage versus the total bill. And regression plots, they can be added to existing axis of subplots without modifying anything else in the figure. So if you had a figure with two subplots, you could use this regplot or regression plot along with other plots, such as like a violin plot. So to show you what I'm talking about, let's go ahead and create a figure of two subplots. So I'll say fig, and then two axes. We'll say axis 1 and axis 2. So I'll set these equal to plt.subplots, and that's how we can create subplots. Whoops. That should be a dot. Okay. Call the subplots method on the plot, and then say what you want the plots to look like. So the number of rows and the number of columns. So I'm going to say 1 row and 2 columns. So 1 by 2 plots, and then I'll say Sherry equal to true, so they align better, and then I will call the regression plot function with the total bill on the x, the tip underscore PECT on the y. We're going to grab that information from tips, and I will set axis equal to axis 1 for the subplot. And then I can also make a violin plot for one of the subplots. And I will have the violin plot be, let's have it be the tip percentage column. And we'll have it be the size of the party. Tips, size, Alright, and then let's choose a color scheme for this. So let's say color equals, and for color schemes, if we want it to be reds, we can pass this, reds underscore R, since there's going to be multiple violins. And then in this case, we'll set the axis equal to axis 2, because it's going to be the second plot over. Alright, so let's go ahead and see what these subplots look like. Oops, and looks like there should be no underscore there. My apologies. There we go. Alright, so using reg plot, you're able to use it in a subplot figure. So here's a figure with two subplots, one regression plot and one violin plot. Alright, and that's it. Next up, we're going to learn about heat maps and clustered matrices. I'll see you there. Hey guys, welcome to lecture 53. This lecture is on heat maps and clustered matrices. Alright, so this is the last lecture in the data visualization section. So let's go ahead. As I mentioned before, Seaborn comes with some great data sets that we can play and learn with. So in this case, we're going to grab a data set called flights underscore dframe. Remember to input all your imports into a cell, the usual ones for the data visualization section. And then we'll set flight underscore dframe equal to SNS load underscore dataset. And the dataset string name is flights. Okay. So let that load. Great. Once it's done loading, let's go ahead and preview it. So we can say flight underscore dframe. And we can check out the first 5 rows. Alright. So what do we have here? We have the year, the month, and the number of passengers that took a flight, either on this airline or on a specific plane. Doesn't really matter for our case. Let's go ahead and pivot this data frame so it's easier to manage. So as we've learned in the last, or not the last lecture, but some couple lectures ago on pivots, we have flight underscore dframe, and we're going to set this equal to the pivot, and we're going to pivot it by month, year, and then the values we want are passengers. So just a reminder about pivot and pivot tables. We set the rows we want, so we want the rows to be months, we want the columns to be years, and we want those values to be filled out with the number of passengers that took a flight. Let's go ahead and show this data frame now. Flight underscore dframe. There we go. So now it's in a much better format for us. Great. And this almost looks basically perfect to make a heat map or a cluster matrix visualization from this. So let's go ahead and show you what we're talking about here. If we want to make a heat map of this data, we just call sns.heatmap, and we're going to pass that data frame through it now. Alright, and now we have a data visualization for a heat map for the passengers. Now let's say you wanted to actually know the number of passengers and annotate each cell with the number of passengers, not just have it be by color. You can do that. So let's go heat map. Again, we'll pass that data frame. And then we'll say annotation equal to true. So in this case, ANNOT equal to true. And let's set FMT equal to D just for some formatting. And there you have it. So now you have annotated each cell with the number as well as the color. So Seaborn is going to automatically try to pick the best color scheme for your data set, and that basically just depends whether it's a converging or diverging color map. So in this case, it's chosen a converging one, so it's gone from a light to a dark, But if you wanted to choose a center, if you will, for your color map, you can do that. So you can specify if you want a center for your color scheme. So to show you what I'm talking about, let's go ahead and do SNS heat map. We'll call the flight D frame on it. We'll set center equal to flight underscore D frame dot, and then we'll get the location. So we'll say LOC, and we'll have it be January 1995. Or 1955, excuse me. 1995. Okay. Alright, so what is this going to do? Well, let's go ahead and take a look. Alt Enter. So now we have a diverging color scheme. So we've created our own center. So white now is going to be at January 1955. Values above that are going to have a more red color scheme. Values below that are going to have a cooler blue color to them. So instead of like the first one where it converges all the way up from 600, now it's diverging from the January 1955 value. So that's how you can choose your color schemes. We can also add heat maps on axis of subplots to make more informative figures. So just like we did with regression plots and the violin plots in the last lecture, we can do something similar for these plots. So let's go ahead and try making a figure with multiple subplots. So I'm going to say F for the figure name, and then let's make two sets of axes. So I'll say axis 1, axis 2. I'm going to set that equal to plt.subplots like we did in the last lecture. So we'll say 2, 1. So in this case there's 2 rows and 1 column. Now I'm going to say, I'm going to call my yearly flights object equal to flight D frame, take the sum. So what I'm doing is I'm taking the sum of all those columns, and the columns are the years. So you can imagine if I take the sums all along 1949, I will have the total number of flights for that year. So that's the yearly flights object I'm making. Okay, so since yearly flights, if you were to look at it right now, it's in a little bit of a weird format. We'll have to grab the values we want with a series and then put them into a data frame. So I'm going to set years equal to pd.series, and I'm going to grab it from yearly underscore flights, and then I'm going to get the index values. And then I'm going to set years to be equal to a data frame. So I'm going to make a data frame out of that series. So I created a series and then ran that series through a data frame. We're going to do the same thing for flights. And this is just to take care of some formatting issues in the yearly flights data. Do a similar thing here. Except in this case, I just want the actual values, not the index values. And we'll create a data frame using that series, pd.dataframe, flights. All right. And now we're going to make the data frame complete and name the columns. So I'm going to say year underscore dframe equal to pd.concat. So I'm going to use a concatenate. And I'm going to put together years and flights. And I'm going to do this along axis equal to 1. And then I'm going to name my columns. So year underscore dframe.columns equal to, so now the columns, let's give them a name. So they should be year and flights. Great. That way they go with each of the series, or I guess they're data frames now that were concatenated together. All right, so let's visualize that data. I'm going to make a bar plot, and you can make a bar plot in Seaborn by passing bar plot. And I'm going to say bar plot of the year. So let's see, bar plot. Whoops. Bar plot year. I'll set y equal to flights, so the total number of flights that year. My data is going to come from the year underscore d frame, so that data frame we just made. And I'll set the axis, or ax, equal to axis 1, because it's on a subplot. And then I'm going to create a heat map below it. So I'm going to say sns.heatmap flight underscore d frame. And then we're going to say, let's go ahead and get a color code or color palette for that. The way we can do that for a heat map is by passing the CMap argument. And in this case, I'm going to choose blues. And you can look at the documentation for other color schemes. We'll also say axis is equal to axis 2, so it goes below. And then something I want to do is, if we scroll back up, we can see that this color bar is set vertical. I want to set it horizontal. So the way I do that is I pass, as we've done before, I can say cbar underscore kws and just pass a dictionary. So in this case, the key is going to be orientation. And I'm going to give its value as horizontal. Alright, so that way the color bar is horizontal. So we've done a lot right now. Let's go ahead and see how we were able to visualize it. Yearly values is not defined. I probably have a spelling error somewhere. Let's go back up and try to catch it. Yearly values, this is in line 8 of flights. So yearly values, I should have written yearly flights. Not sure why. I see. I wrote that twice. That should have been flights. Okay, now let's try it. Okay, there we go. Alright, so now I have my bar plot on top, and I have my heat map on the bottom, and my color bar has been oriented horizontally, so it's on the bottom as well. And you can see now that the years match up, and you can get a really nice data visualization here. So that's great. Finally, we're going to learn about using a cluster map. So let's go ahead and create one. So a cluster map is going to reformat the heat map so similar rows are next to each other. So I'm going to say sns.clusterMap of that data frame, so flight underscore d frame. Okay, and here we have our cluster map. So if you notice, the months are no longer in order. January, February, November down here, December's over here. But in this case, similar rows are next to each other. And you can see they're grouping and linking, they're clustering, if you will, on top and on the left. And here you have your color bar scale. Okay, so let's go ahead and just uncluster the columns. So we can do that by saying sns.clusterMap. Let's pass flight d frame again. And in this case, I'm only going to cluster by the rows, so I'm going to call col cluster equal to false. See what that looks like. Okay, so now I've only done it by the rows, so by the actual month. We don't care about the years themselves. We'll keep those independent of each other. So it's only being clustered by the month. All right, so since the number of flights increase every year, as we saw above, if we scroll up a bit, you can see the number of flights is increasing every year. So we should set a standard scale. So let's go ahead and standardize. So I can do that by saying sns.clusterMap, say flight underscore d frame, and I'm going to set a standard underscore scale and set that equal to 1. So now what that means is I'm going to standardize by the columns or by the year. So let's go ahead and do that. All right. So now what do we see here? You can really tell now that the summer months are the heavier usage months, since everything's been standardized by the year. Now if you look at your scale, it goes from 0 to 1. So here we've eliminated the problem of flights increasing every single year. We could also scale it by rows. So we could say sns.clustermap flight underscore dframe, so pass the data set, and then set the standard scale underscore scale equal to 0. And this would then scale the rows. All right, great. And then finally, we can also normalize the rows by their z-score. So this is going to get a bit into some heavier statistics, but this subtracts, so what a z-score does, it just subtracts the mean and then divides by the standard deviation of each column. So then the rows have a mean of 0 and a variance of 1. So this is going to be the very last thing we go over. So it's going to be cluster map flight underscore dframe. And if you want to normalize by their z-score, you just input the argument z-score equals to 1. Again, what the z-score does, it just subtracts the mean and divides by the standard deviation of each column, so that the rows have a mean of 0 and there's a variance of 1. And so this is what the result looks like. So you can really tell that it's the summer months are where you have higher number of flights. Okay, so that's it for heat maps and clustered matrices. You should give yourself a huge pat on the back. You've made it all the way through lecture 53. Great job. Next up is a whole new section, and we're just going to be doing projects that you can do to add to your portfolio, and we're going to be using real data sets. We're going to take all the tools we've learned and hammer out some great data analysis projects. I'm really excited for you and the next section. Let's do this. Congrats again on finishing all the way up to lecture 53.